Hello everyone, welcome back to Z Physics. Today we're going to be going through a tricky circular motion question. In particular, this is a circular motion at an angle question. So we have a circular racetrack which has a banking of 15 degrees and a radius of 1 kilometer. So if we had a race car, at what speed must the car be driven if there's no tendency to side slip along the racetrack? By side slipping, what I mean is that if we imagine the banking to be across here, we don't want any lateral movement within the car. So this over here is the banking along the racetrack, and this here is our car, and you don't want the car to be moving along the banking. This will be a perfect opportunity for you guys to pause this video and attempt the problem. Okay, now that you have definitely paused the video and you've attempted the problem and you have an answer, no, seriously guys, you must pause this video and actually try to solve this problem. Okay, well, now let's have a look at our solution. So first off, let's think about the forces involved. Because we have an angle of 15 degrees of the actual banking, this would mean that the normal force will also be directed at an angle. So we can draw our normal force, which will be at 90 degrees to this surface. So it's going to be along here somewhere. Now the normal force will have a horizontal and a vertical component. The weight will be acting just straight down. I can draw the weight just here. Okay, so this over here is our weight. This is just mg, and I'm going to call my normal force just n. Let's draw that vector a little bit shorter actually. So I'm just going to zoom in and just take a little bit off the normal force. Okay, well, the normal force n will have two components. It will have a horizontal component and it will have a vertical component. So let me just draw the vertical component first, which will be along here. The vertical component will be pointing upwards, and this will balance out the weight. In fact, I could even write down that, let's say the y component of n, let me just switch back to this white pen just here, or silver, ny will be equal to mg. So because our car is not falling, it is not side slipping either, then mg will have to equal to this blue vector ny. It will also have a horizontal component, and let's draw that as well. Let's pick, I think that's orange. So let's say that the car is moving this way, and that component will be, let's call that nx. Nx will be providing the centripetal force, which is mv squared divided by r. Now, if we think about similar triangles, we can actually pretty easily prove, I'm not going to do this in the video, but that those two triangles are similar, and this angle here is actually equal to this angle there. So this angle here is 15, which turns this component, the vertical component, to be n cosine theta, or cosine 15, and this angle here, or this component here, will be n sine of 15, because it's the opposite angle. So actually what we can do is just simply rewrite our equations here. So rather than ny, I'm going to say that n cosine of 15 is equal to mg, and n sine of 15 is equal to mv squared divided by r. Okay, now we have a system of two equations that we can solve. let's just solve the first equation for n, and then I'm going to substitute that in the second equation. So from the first equation, what we can infer is that n will be equal to mg divided by the cosine of 15 degrees. And then what I'm going to do is just substitute that back into this equation. So what I'm going to get is that mg over cosine of 15 times sine of 15 is equal to mv squared divided by r. Now notice that the masses are going to cancel out, so we don't need to worry at all about the mass of the car, which is brilliant because that's not given actually in our question. Well, now that we have a good expression for the velocity, what we can do is just simplify this a little bit further. We can remember that sine over cos is actually equal to tan. So what we're going to get is that g times the tangent of 15 is equal to v squared divided by r. Rearranging for v, we're going to get that v is going to equal to the square root of gr tan of 15, which is going to equal to the square root of 9.81. The length of the radius of the racetrack was 1 kilometer, so that's 1,000 meters times tan of 15, which is equal to about, what's happened here? Let's go back to my equation. If we put that into a calculator, we are going to get about 52.3 meters per second. Okay guys, so just to recap, we had this problem. We had a circular racetrack that has banking of 15 degrees and a radius of 1 kilometer. At what speed must the car be driven if there's no tendency to side slip? Side slipping means that the car is not moving up or down essentially, which means that this component of the normal force is going to balance out the weight. Because the normal force is at an angle now, then it will have two components, and cosine of 15 is always going to be the vertical component, and the horizontal component will provide the centripetal force. Ny is equal to mg and x is equal to mv squared over r. And then we have this system of equations with n cos 50 because that's the adjacent component, and sine of 15 because that is the opposite component to this angle. Then we play around with the equations, we cancel out the masses, and we got a value for the speed to be over 50 meters per second, which is pretty fast. Hopefully you've enjoyed this video and you found this useful. Thank you very much for watching, and I'll see you in the next video.